everyone. Today's session is on application to the coupling problem. So, the first problem states that there is one slot antenna and it consists of a slot in a conducting ground plane as shown in the figure. Okay, so, there is a slot present. The length of the slot is given by L and the width is W, and the length of the slot is along the Z direction, whereas the width of the slot, that is W, is along x direction. Okay. It is assumed that Ex equals to Vm upon W sin of k L by 2 minus Z is in the slot, and we need to obtain the magnetic current equivalent. Also, we need to show the radiation field for small w. Okay. So, we will start solving it. So, we are given a slot antenna. Okay. So, we will start with Okay. So, basically it is a dipole slot antenna when fed by a voltage that is impressed across the center of the slot. Okay. The slot and the ground plane, it can be viewed as a transmission line, and the field in the slot will be essentially a harmonic function of kz. Okay. So, basically we were given a slot of length L and width W, and this is Z. Okay. So, in the question it has been asked that we need to assume Ex as, so Ex is Vm upon W sin of k L upon 2 minus mod Z. So, this is provided to us. So, what we will do now, we will take the help of equivalence principle, okay, and then solve the problem. So, basically we can start with like using the equivalence principle. Using the equivalence principle, what we can do, we can replace the aperture by a patch of magnetic current. Okay, so, we can write that using the equivalence principle, we will replace the aperture by a patch of magnetic current. Okay. Now, then we can say, like suppose this was Ex. So, this is the slot, this is Ex. So, we can write this. So, this was our original problem. We have a slot on the conducting ground plane. So, this is our original problem. Fine. So, here is the unit, n cap is y cap, normal. Now, this original problem, what we will do, by using the equivalence principle, we will replace the aperture by a patch of magnetic current. So, the next step, if this is A, this was our original problem. Now, what we will do, we will replace the aperture by a patch of magnetic current. So, now it will look like, so we have replaced this aperture by magnetic current. Okay. So, ms is the magnetic current. This was our N, and denote this. Okay, then we can say in this we have applied the equivalence principle, and let us write this as aperture removed by using equivalence theorem. By using equivalence. Okay, so this is B. Now this ms, okay, we know this is E cross N. Okay, here we have N is Y, E is X. So X cross Y we will get as Z. So ms is E cross N. So this state is when we have removed the aperture by the equivalence and we have replaced the aperture by a patch of magnetic current. Next we will apply the image theory. For that, this will be like this. So here we can write. Now while we use image theory, so this will be, this we can write as conductor removed by image theory. Now see, while we have removed the aperture and placed the magnetic current over there, okay, so now what happens is that in the vicinity of the ground plane there is magnetic source. Okay, in the vicinity of the ground plane we have the magnetic source. Okay, now therefore now if we apply image theory, okay, in this state, that is in figure C, if we apply image theory, then what we will have, then after removing the ground plane there will be the image, and both of them are in the image and the actual will be in so vicinity that it can be assumed as like this, twice of ms. Fine. So therefore we can then write ms as twice of Vm upon W sine of K L by 2 minus Z. Okay. So this was the magnetic current equivalent. The first part is now obtained. Now what the second part says, it says that if we assume like W is very small, then what will be the radiated fields. Okay. So now previously the slot was like this, it was having a width of W and this was the length of the slot. Now it has been said that we need to assume W is very small, that is W when tends to 0. Okay. Now when W tends to 0, we can say like we can draw like this. So when we change the original problem to this state, like when conductor is removed by the image theory and we have 2 ms. So this state we can draw like this. So basically we were having this as Z, this is Y, this is X, and this was 2 ms. Okay. Now when W is made very small, okay, what will happen, the equivalent magnetic current, this one, the equivalent magnetic current will then behave as a line filament. So, now we can draw this problem like this. So, this will be Z, this is Y, this is X, and since W is tending to 0, so at origin we will have this. Okay. So, now we know that the radiation field for dipole, the radiation field for dipole, we can write for the current distribution of the radiation field can be written like E theta as j eta minus j k r upon 2 pi r cos of k l upon 2 cos theta minus cos of k l upon 2 by sin theta. So, this was the radiation field for dipole. Okay, considering in this case the current distribution used to be Iz is Im sine of k l by 2 minus z. So, basically with this equation, if this is equation number A, so now the radiated field for this figure for mz we can write down using the duality. So, by using the dual of equation A, equation number A, okay, and here we have, and we can write like making the following substitution. So, we will use the dual of equation number A and we will substitute in place of Im. Now, we have 2 Vm. Okay. So, now using duality from equation A, we can write E theta will be H theta since we are applying duality. So, H theta will be, okay, in place of J we will have J, in place of eta we will have 1 upon eta since we are applying duality, and then in place of Im we have twice of Vm e to the power minus j k r upon 2 pi r cos of k l by 2, sorry, it will be k l by 2 cos theta minus cos of k l by 2 upon sin theta. Okay. So, thus we will have, so this 2 will cancel out. We can write down like j Vm e to the power minus of j k r upon eta pi r cos of k l by 2 cos theta minus of cos k l by 2 upon sin theta. So, this is equal to h of theta. Okay. So, this applies when we are considering y greater than 0, and if we consider y as less than 0, this will be minus of h theta. So, this is the radiated field. Okay. Now, let us move to the next question. The next question says that there is one coaxial line and it is opening onto a ground plane. Okay. So, here we have a coaxial line which is opening onto a ground plane, and again it has been told that we need to assume that the field over the aperture is given as E rho equals to minus V upon rho log of B by A, where B is the outer and inner radius that we can see from the figure, and then we need to obtain the equivalent magnetic current over the aperture. So, we will solve this problem in a similar manner using the equivalence principle. So, let us start solving this. So, it was given like we have a coaxial cable this is the inner radius A and this is the outer radius B. This is Z, Y, X, and we have a ground plane over here. Okay, this angle is theta. Now, in the question it is asked, so basically this was our original problem given in the question. Okay. It was asked, it was told that the field over the aperture was given by, it was been told in the question that is E rho is minus V upon rho log of B by A. Okay. So, where A and B are the inner and outer radius of the coax, and V is the line voltage. Fine. Now, so what we need to do? We need to again using the use of using the equivalence principle, we will change the problem, original problem, into the equivalent problem. Okay. So, basically what we have a coaxial transmission line that is being opened into a ground plane. Okay. So, it is to be noted like that in the question it is assumed E rho is this one minus V upon rho log by A. Now, we can change this original problem, we can draw like this. This is our, this is Z, this is Y, this is X. This aperture will be replaced, this aperture by magnetic surface current. So, we can write like this MS. Okay. MS exists, where it exists? MS exists only over the aperture. MS exists only over the aperture, that is the coax opening. Okay, so MS exists only over the aperture for tangential E is 0 over the ground plane. Okay, so we can write like this. So we will have, we know M is E cross N. So E is rho, N is Z. So rho cross Z we have minus phi. Okay. So M phi will be like this. Okay. So this is now M phi. So this is R, this angle is theta, and this will be phi. So now we can write, so this is the equivalent problem. So now we can write M phi as V upon rho log of B by A. So this is this M phi. So basically what it is, this is a loop of magnetic current which, if B is very less than lambda, can act as an electric dipole. So we can write this is a loop of magnetic current. This is a loop of magnetic current which the condition is, if B is very less than lambda, acts as an electric dipole. Acts as an electric dipole. Okay. Now this current is visualized like a say a continuous distribution of magnetic current filaments, in which the strength we can write like dk is M phi d rho. Okay. So then the total moment of this source, then we can write the total moment of the source is, we can write it as Ks is integration of pi of rho square dk. So that can be written as pi rho square, in place of dk we will substitute M phi d rho, which will give us pi rho square. In place of M phi we have V upon rho of log B by A d rho. So basically we will have pi V upon log of B by A. So this integration will run from A to B rho d rho. Okay. So then we can have Ks as pi V upon log of B by A to B rho d rho, which will give us pi V upon 2 log B by A B square minus A square. Okay. Now this magnetic loop we can, this is an equivalent to electric dipole if we make certain substitution like IL equals to minus of j omega epsilon Ks. Okay. So in place of Ks, then we can substitute this value and then we can eventually find out all the fields. Okay. So this is all for today. Thank you.